In the world of aerial warfare, there is a fundamental law of physics that dictates survival. If a radar can see you, it can kill you. For decades, the problem of the radar cross-section, or RCS, was the ultimate bottleneck in aviation. To move air, you need wings. To carry fuel, you need a fuselage. To change direction, you need a tail. But every 90-degree angle and every vertical surface acts as a corner reflector, bouncing electromagnetic waves directly back to a receiver with the clarity of a lighthouse. To achieve true stealth, you have to defy the traditional silhouette of flight. You have to remove the tail. But physics doesn't like that. Without a vertical stabilizer, an aircraft is naturally unstable. It wants to swap ends and tumble through the sky. Yet, tonight, a single pilot, one of the few women qualified to command this $2 billion platform, is loitering over the Middle East in a craft that, on a radar screen, appears no larger than a common honeybee. The B-2 Spirit wasn't just built to be invisible, it was built for endurance. In the Middle East, the strategic challenge is the anti-access/area denial, A2/AD, bubble. Modern S-400 surface-to-air missile systems create a no-go zone for conventional fourth-generation fighters. The mission for our pilot isn't just a sprint, it's a 30-hour marathon launched from Missouri, requiring multiple mid-air refuelings. But why use a flying wing? Why go through the engineering nightmare of a tailless design? It comes down to specular reflection. $RCS equals \sigma equals \frac 4 pi a squared a lambda caret 2 $. In simple terms, the area $sigma a radar sees is determined by how much energy is reflected back. A vertical tail is a disaster for this equation. To solve this, Northrop Grumman engineers used planform alignment. By ensuring every edge of the aircraft is aligned to the same two angles, radar energy isn't scattered in all directions. It's concentrated into two very narrow spikes of reflection. If the radar isn't at the exact millisecond perfect angle to catch that spike, the plane is effectively invisible. Host, VO, but how do you fly a plane with no tail? This is where the engineering hero moment occurs. The B-2 uses split-brake rudders. Visual, close-up of the B-2 wingtips. The flaps split open like a bird's beak. When the pilot needs to turn, the aircraft doesn't use a vertical rudder. Instead, the wingtips split open to create differential drag. However, because the B-2 is inherently unstable in the yaw axis, a human could never react fast enough to keep it straight. The digital tail is a quadruplex fly-by-wire system. It samples the atmosphere hundreds of times per second, making micro-adjustments to the flight surfaces before the pilot even feels a gust of wind. It is a masterpiece of control theory over aerodynamic stability. But real engineering is a game of compromise. To maintain that stealth profile, the B-2 cannot use an afterburner. The engines are buried deep within the fuselage behind S-duct intakes. This prevents radar from hitting the highly reflective spinning fan blades. But this creates a massive cooling problem. Without the cooling airflow of a traditional fighter, the B-2 must use its fuel as a heat sink, cycling it through the airframe to soak up the thermal energy produced by the electronics and engines before it's burned. Furthermore, the skin of the aircraft is covered in radar-absorbent material, RAM. This isn't just paint, it's a polymer infused with iron ferrites that convert electromagnetic energy into heat. The downside? Maintenance. For every hour the B-2 spends in the air, it requires over 50 hours of specialized maintenance on the ground. The material is so sensitive to moisture that the hangars must be climate-controlled. In the humid environments of the Middle East, the invisibility literally starts to peel off. So, is it worth it? At $2.1 billion per aircraft and an hourly operating cost of $130,000, the B-2 is the most expensive way to deliver a payload in human history. But as our pilot clears the AO, area of operations, and begins the 15-hour flight back home, the economic reality becomes clear. One B-2 carries the payload of a squadron of F-35s, requires zero forward base infrastructure in the conflict zone, and, most importantly, is the only platform that can bypass a $500 million missile battery with the stealth of a mathematical equation. The B-2 Spirit is a reminder that we can overcome the fundamental limits of aerodynamics, provided we have the computing power to simulate what nature never intended to fly. If you want to see how the next generation of stealth is being built with the B-21 Raider, click here. Or, if you're interested in why we still use 1950s technology for the B-52, check out our video on engine longevity. Would you like me to dive deeper into the specific materials science of radar absorbent coatings?